In this video, we're going to discuss convergent plate boundaries, including their characteristics and examples. So to watch this video, just make sure that you have a copy of the PowerPoint presentation that goes with the video. And you can stop or rewind the video at any time as you need to. So first, I'm going to show you an animation of convergent plate boundaries. And as I show the animation, I'll add a few comments. So in this animation, you have a cross-section of a convergent boundary. On the left and on the right, you have thick slabs. So these would represent a continental plate. And then in the middle, you have a gray, thinner slab, which would show the oceanic floor. And then in blue, you have the ocean. So this is a cross-section. And then at point X, you have what we are going to be calling a trench, an oceanic trench, not to be confused with oceanic ridges. Remember, the ridges are mountains where seafloor spreading is occurring, and these are divergent boundaries. Here, this is a trench, so it's not a mountain, but rather it's a big trough on the seafloor, a big low point. So you see the arrows show these two plates that are going to be converging. So the plate on the left includes both the continent and the oceanic floor. That's all part of the left plate. And then the plate on the right only includes the continent on the right-hand side. So as these two plates are converging, notice what happens to the seafloor. It plunges down underneath the other plate in a process that we call subduction. And notice that now point Y represents the trench. And what they're trying to show here in this video is how the plate on the right has moved in relation to the plate on the left. And we can't really say whether, one is moving more than the other one. All we know is how much they move in relation to one another. So you also have an illustration of the convergent plate boundaries in your textbook. And actually, there are three different illustrations that we're going to refer to. So at convergent plate boundaries, if we want to describe the motion, we would say that the plates move toward one another. And then in order for plates to move towards one another, you need compressional stress. You need forces that are going to come towards one another, and we refer to that as compressional stress. So the compressional stress kind of shortens the plates, and is in this compression and shortening, the plates will see they form mountains. At least one of them will form mountains. So there are three types of convergent plate boundaries. So you could refer to these as subtypes of convergent plate boundaries, but it's really important to understand the differences between the three types. So when we describe the three types, it depends on the type of crust on either side of the boundary. So we have to consider whether we have oceanic continental convergence, meaning one plate has oceanic crust, the other has continental crust. Whether we have oceanic convergence, both plates with oceanic crust, or continental convergence, both plates with continental crust. And the reason we describe those three subtypes is because they are quite different, and they result in very different features at the surface of the Earth. So all the convergent boundaries are in figure 3.18 in your textbook. So first we're going to consider oceanic continental convergence. And so you see on this particular block diagram, you have a plate on the left with oceanic crust, and then you have a plate on the right with continental crust. So this is oceanic continental convergence. Now remember that the oceanic crust is made of basalt, which is slightly denser than continental crust, which is on average made of granite. So, and this difference in density is very significant because oceanic crust is dense enough to actually go back down into the Earth. It's able to go back down in a process we call subduction. Continental crust is not dense enough to go back down. So continental crust never subducts. It never goes back down into the Earth. So when you have oceanic continental convergence, the plate with the oceanic crust is going to be subducting. So it bends and it subducts into the earth. Where it bends, it tends to form a trough on the seafloor, and that's what we call the trench. In this particular block diagram, the trench is not very clear. A lot of it has been filled up by sediment that has been scraped from the seafloor. Okay? Because as these two plates converge, you have the continental crust here, the oceanic crust has stopped ducting. Well, this is not an easy process, and it's scraping sediment. Some of that sediment goes back down into the earth, but some of it gets scraped off and kind of fills up the trench. So, again, we have two plates. Oceanic plate is going to subduct. Continental plate is going to stay where it is. So as the oceanic plate subducts, it gets hotter and hotter because temperature increases in the Earth. So at some point, and usually it's about, I think, 100 miles or so of depth, it starts to melt because the temperature is increasing. So the subducting plate starts to melt. It also releases water under pressure, and that release of water under pressure generates melting in the asthenosphere that is above the subducting plate. So when you see on this illustration on the right of the subducting plate where it says mantle asthenosphere, magma created here. So you have magma that's generated here, both because the subducting plate is melting and because the wedge of asthenosphere there is also melting. So you have a lot of magma generated in this area, and magma is buoyant, so it's going to slowly move towards the surface. As it moves towards the surface, two things are going to happen. So some of that magma will reach the surface and will form volcanoes on that continental plate. So it will form volcanoes on the continent. But also the magmas that are generated are very hot magmas. And when they go through the continental crust melts at a much lower temperature than the temperature of the rising magma. So there is melting in the continental crust. So you have magmas that are generated at the subduction, deep at the subduction, but you also have magmas that are generated within the continental crust because you have the source of heat for those magmas is the magma that's rising from the asthenosphere. So you have two places where magmas are generated. So the magmas that are generated in the asthenosphere are very hot. They come up to the surface, they transfer some of that heat to the crust and melt the crust, and they reach the surface and form volcanoes. The magmas that form within the crust, within the continental crust, those are thick, cooler magmas, and they usually just solidify in place, so they don't usually come up all the way to the surface. The area, the whole continental area, so that is at the surface above the subducting zone, we call this a continental volcanic arc. So continental because it's on the continent, volcanic because you have volcanoes, and it's called an arc because those chains of volcanoes are typically not linear, but they are arcuate, and that just has to do with the sphericity of the Earth. Those continental volcanic arcs are mountains. Now, why are they mountains? Again, we have that compression, we have this oceanic plate subducting, but the continental plate is being compressed, so it's being shortened and lengthened in the height dimension, if you wish. So it forms mountains. So on the next slide, we're summarizing the characteristics of oceanic continental convergence. So the oceanic plate is the one that subducts. You form a continental volcanic arc, so that's a chain of mountains on the continent with volcanoes at the top. You have volcanoes at the surface, but you also have intrusive activity, meaning formation of rocks that formed by the cooling of magma at depth. So you have intrusive activity with granites forming at depth. And general or global geologic processes that occur are volcanism. You're going to have earthquakes. That subduction process creates a lot of friction, and it doesn't just move slowly and surely, but rather it moves in jerks, and every jerk is an earthquake. And you have mountain building because of the compression process. Examples, active examples of convergent boundaries that are oceanic continental. Well, one is very close to us. It's the Cascade Range of Washington, Oregon, and Northern California. Okay, so the furthest south volcano in that arc is Lassen Peak. And then the Andes Mountains of South America. So the Andes Mountains are pretty much all along the west coast of South America, and they are created because of this oceanic continental convergence, and they are characterized by volcanoes. So one thing to remember is that at depth, so you have the volcanoes at the surface, at depth you have granite that is forming, because you have magmas, the continental crust is being melted, and then it crystallizes as granite. So you have a lot of intrusive activity forming at depth. So this is a picture of Mount Shasta in California, which is an active volcano in the Cascade Range, or you could call it dormant. It's not actively erupting now, but it erupted I think it's less than 200 years ago. As we know, had a big eruption in 1980. And it's been pretty active since then. No major eruption like in 1980, but some small eruptions. Here we see some steam coming out. Okay, so next we're going to talk about oceanic convergence. So in this illustration, which is also from figure 318, you see two plates, but now both plates are oceanic. So in this case, the subduction could have gone either way. So here, the subduction is showing that the left plate is subducting to the right, while you could have had the right plate subducting to the left. What determines which plate subducts? It may be something that's happening farther off. Who knows? But the subduction really could have gone either way because you have two oceanic plates, so either one could subduct. So as the plate that's subducting gets deeper and deeper, again, the same processes are going to happen as in oceanic continental convergence. Okay? So the subducting plate is going to melt, and then the asthenosphere above that plate is going to melt. So you're generating magmas, and these magmas are working their way towards the surface. In this case, the surface is going to be the bottom of the seafloor, at least at first. As the rising magma goes through the oceanic crust is made of basalt. It melts at high temperature, so it doesn't. Those rising magmas are not going to melt the oceanic crust. Remember, in oceanic continental convergence, there was melting of the continental crust. Here, the rising magmas are just coming up, and they are just going to erupt. So at first, they'll erupt on the seafloor, and then as the process goes on for millions or tens of millions of years, eventually that volcanic activity is going to stick up above sea level and is going to start forming islands. And those islands are volcanoes. So the feature that we'll see at the surface when we have oceanic convergence is a chain of volcanoes, and we refer to that as a volcanic island arc. Again, because usually those chains of volcanoes are not going to be straight in a line, but rather they are going to describe an arc. So processes that go on with oceanic convergence, either plate could subduct. You form a volcanic island arc, so it means an arcuate chain of islands with volcanoes on top. So you have volcanic activity. You have earthquakes too, because the subduction process is going to be similar to what we have with oceanic continental convergence. Again, it's a jerky process. The plates kind of stick together, and then they release one earthquake at a time. And some mountain building, that plate that is staying on top where the volcanoes form, eventually, you know, those volcanoes, they really form to be mountains, and the plate is compressed a little bit. You don't have such high mountains as you can have on the continent, but when you look at those islands, which are within volcanic island arcs, they are very rugged. They are not flat features, so there is some mountain building going on as well. So examples that you need to know and be able to locate are the Japanese islands. Okay, these are the result of oceanic convergence. The Aleutian Islands that are at the tip of Alaska, they are the result of oceanic convergence. The Philippine Islands, which are in the Pacific Ocean, Mariana Islands, and Indonesia is, the Mariana Islands are in the Pacific Ocean, and the Indonesian islands are in the Indian Oceans. And now I will show you the location of all of these on the map in a few moments. So this is a picture of the volcano on Augustine Island, which is part of the Aleutian Islands, so that's part of Alaska. So the third type of convergent boundary is when we have two continental plates that meet, and in this case we say they collide. We call that a collision. The thing is, it's not like you have a continent and then suddenly the continent is going to move like this, like converge on itself. Continental convergence evolves from oceanic continental convergence. So if we look at this illustration, which is the same illustration as the other convergent boundaries, but now it's figure C, you see on the left you have a plate with all the black arrows. So let's say this is plate 1. And then on the right you have a plate. Small plate is a very small portion of this illustration. And so the plate on the left, plate 1, has a continent on the far left, but it has oceanic crust. And right now this oceanic crust is subducting actively underneath plate 2, which is on the right, so underneath this continental plate. So right now we have oceanic continental convergence, so we would have a continental volcanic arc at the top of plate 2, on the continent that is on plate 2 on the right. You see a trench, so again the trench is a trough at the bottom of the ocean. But because plate 1 on the left has a continent on it, that's right now is far off the boundary, but over time, over millions of years, eventually as the ocean gets subducted, okay, the two continents get closer to one another. And eventually, over time, you get what's going on in figure D, which is that the continent on plate 1 is now colliding actively with the continent on plate 2. Okay? So the boundary in illustration D could be considered this whole area of mountainous area, or any one of these faults that are shown with half arrows over the continent. So at this point, the two continents have merged together, and but you still have two plates, because plate 1 on the left is still pushing against plate 2 on the right. But because you have two continents pushing against one another, and they can't subduct anymore. They are too, remember the continental crust is too buoyant. So they stay aloft, they stay on top both, but they really they're working hard to try to, because they're moving in opposite direction. So as a result, because no plate is subducting, you don't have subduction anymore, so you don't have volcanic activity anymore, but you still have a lot of earthquakes and a lot of mountain building, because these continents are pushing against one another and they have no other way to evolve than to go up. So these actually form the highest mountains of the surface of the earth, these types of boundaries. So the continents go up, and notice all the faults at depth, so they crack and they just kind of move up and just get taller and taller. Now, of course, as they get taller and taller, erosion takes them down in elevation, so that there is not an infinite number of elevation or that they can reach. So again, at these continental convergent boundaries, the main thing is now subduction stops because continental crust cannot subduct, and you get very tall mountains, and you have a lot of mountain building going on, and you have a lot of earthquakes as well. And the earthquakes at these types of boundaries can actually be felt very far from the boundary because you have this very strong continental plate that's just creating tremendous stress and pressure, and when that releases, it can be felt very far within those plates. So in continental convergent boundaries, again, subduction stops, but it evolves from oceanic continental convergent boundaries. And you have earthquakes, very strong earthquakes, as well as mountain building, and mostly very big mountains that form. So the best example nowadays are the Himalayas, which are at the between Nepal, where Nepal meets China. So the Himalayas are actually in both China and Nepal. Also, the Alp mountains of Europe are part of the same process. And then, but they're not as active as the Himalayas nowadays. And then there are some old examples. So the Appalachian Mountains in the eastern side of the US, these formed when Pangaea formed. Okay, so when the continents came together and formed Pangaea, well, when continents come together, that's continental convergence. So the Appalachian Mountains, at the time that they formed, they would have been as mighty as the Himalaya Mountains now. There is another chain of mountains in the middle of Russia called the Urals, and those also formed at the time that Pangaea formed. So this is a picture of the Himalayas, and kind of almost in the middle, the highest peak in the background is Mount Everest. So Mount Everest is the highest peak, highest mountain in the world. So it's part of the Himalaya Mountains, and which are forming as a result of continental convergence when India collided with Asia. And this process is still going on. So on this map, I have, I'm going to show you the location of the different examples that you need to be able to know and refer to continental plate boundaries. So first, we have examples of oceanic continental convergent boundaries. You have the Andes Mountains of South America and the Cascade Range of Washington, Oregon, and Northern California. So another thing that when you get actually to your lab on plate tectonics, you will have to locate different examples of that are related to plate tectonics, not necessarily these same examples. These are the ones that you need to know that you could be tested on exam and quizzes, for example. And when you list those examples, you're going to have to list the plates that are at that boundary. Okay. So, for example, if I look at the Andes Mountains, now I've shown the Andes Mountains. The Andes Mountains are on the continent. That's the actual continental volcanic arc. The boundary itself is where this line has been drawn with little triangular triangles on the side of the line. The line itself shows the actual boundary, and then the little triangles show the direction of subduction. Okay. So in the Andes examples, we have the Nazca Plate to the west is subducting beneath South America to the east. So the trench would be located at the boundary, which is the line that has the triangles, and the continental volcanic arc is this red outline that I have drawn over South America. The Cascade Range is again a continental volcanic arc, which represents the the surface feature of the convergence of the Juan de Fuca plate to the west, this very small plate to the west of North America. And then to the east of the boundary, we have the North American plate. So the small oceanic Juan de Fuca plate is subducting beneath the larger North American continental plate. So next, several examples of oceanic convergence that you also need to know. So the Japanese island, which I have highlighted in green. The Aleutian Islands are these dots at the end of the Alaskan Peninsula. The Mariana Islands are the dots that I have drawn to the left of this convergent boundary with triangles. The Philippines are the red islands, and then the Indonesian islands are the purple islands. So the Japanese islands are convergence. Again, all of these green names represent oceanic convergent boundaries. For the Japanese islands, you have the Eurasian plate converging. Now you notice that it changes in the northern area, it's converging with the Pacific plate. And in the southern area of the Japanese islands, it's actually converging with the Philippine plate. Now, according to the triangles, we see that the Pacific or the Philippine plate is the one that's subducting beneath the Eurasian plate. For the Mariana Islands, we have convergence of the Pacific plate with the Philippine plate. The islands are on the Philippine plate. The triangles are pointing towards the Philippine plate, so it means the subduction is of the Pacific plate. It's the Pacific plate that's subducting westward beneath the Philippine plate. For the Philippine Islands, it's between the Eurasian plate and the Philippine plate, and notice now, this one doesn't make any sense because the islands have to be on the overriding plate. So I think that the triangles have been drawn on the wrong side. Remember, in your convergence, you have one plate that subducts, and then the other plate is the one that has the islands. Okay? And the triangles normally on these converging boundaries point into the direction of subduction. And then the Indonesian islands, these are the convergence of the Indian-Australian plate underneath the Eurasian plate, and the Indian-Australian plate is the one that's subducting, and the Eurasian plate is the one that has the islands. And finally, the one example of continental convergence you need to know are the Himalayas, which are weirdly now, there is no subduction here, even though they show little triangles at the boundary, but remember the Indian plate is the one that had the oceanic crust that eventually all subducted under the Eurasian plate, and at that point India and Asia collided and formed the Himalayas. So the Himalayas, if you wanted to really draw them, you would draw like an oval over the boundary here. So on the next slide, I'm going to list the plates that are interacting at these boundaries. So this would be a good time for you to stop the video, look at your map with the different plate boundaries, and figure out which plates are interacting at those boundaries. And then when you're ready, you can continue the video. So here I'm listing the plates that are interacting at the different boundaries. I'm not going to go over it, and you can just pause the video to check your answers. So finally, just a few questions about convergent boundaries. So the first question, which of the following statement is not true about convergent boundaries? A, the Andes Mountains are an example. Well, that's true. The Andes Mountains are oceanic continental convergence, so they are an example of convergent boundaries. The crust is shortened. Yes, the compression process shortens the crust. There are 3 types of convergent boundaries, depending on the type of plates involved. That is true. Plates move toward one another. That is true as well. Tensional stress is characteristic. That's the one that is not true because we need compression to form a convergent boundary. The Andes Mountains are an example of, is it divergent boundary? Oceanic convergent boundary, oceanic continental convergent boundary, or continental convergent boundary. The Andes Mountains are an oceanic continental convergent boundary where the oceanic Nazca plate is subducting beneath the South American continental plate. Subduction occurs at divergent boundaries. No, we have seafloor spreading. They are not subduction. Oceanic convergent boundary. Yep, there is subduction there. Oceanic continental convergent boundary. There is subduction there as well. Continental convergent boundary. No subduction. So it's both B and C. So which the answer is E, of course. Okay, so next question. Volcanism occurs at divergent boundaries. Yes, seafloor spreading is a volcanic process. Oceanic convergent boundaries, certainly. Again, think of islands such as the Aleutian Islands, Japan, the Philippines, the Marianas. You're going to have volcanoes because of that oceanic convergence process. Oceanic continental convergent boundary, think of the Andes Mountains, the Cascade Range. These have volcanoes, so yes, there is volcanism there. Continental convergent boundary, no, the Himalayas, no volcanoes. So the answer is A, B, and C, so the answer is F.